I'll be there from 8 to 10 a.m. And 12 to 12:30. That's about it tomorrow.
Okay, folks. Today what we're going to be going over is we're going to be going over the
Lewis acid base definition, or I'm not Lewis. Well, yes, we're going to go over the Lewis acid base definition. We're going to look at some examples and figure out how to predict who the Lewis acid and who the Lewis base is. Then we're going to talk about salts, because salts can be classified as acidic, basic, or neutral. And when we get to the salts, we're going to go back to, I'm going to demonstrate how you can take a salt and figure out whether it would be considered an acidic salt, basic salt, or neutral salt. I actually looked at the schedule, and amazingly enough, we are slightly ahead of schedule. That doesn't mean I'm going to, what it means is I'm going to go ahead on Friday and start introducing the concept of buffers, which was originally supposed to be Monday's discussion. Now, the reason I'm going to do that is it'll allow me to slow down when I start doing titrations with you, which those are a bigger topic. And I would have had to move pretty quickly through strong acid, strong base titrations, because doing a weak acid titration will take the entire class period to do one. Doing a weak base titration will take the entire class period to do one. So this kind of allows me to slow down a little bit when I get to the titrations, but not, I mean, it's only going to give me one extra class period, essentially. So. And I apologize for missing yesterday. It wasn't something I wanted to do. But hopefully, well, I know a lot of people got a lot of work done on their service learning project, because I saw a lot of GroupMe flying around. Something like when I opened my eyes, I had 60 in my inbox. So I know there was a lot of discussion going on. So hopefully that actually assisted you in getting the service learning project really honed in, so that you don't have to do much before 11:59 p.m. tonight. So, okay. Any questions before I get started? We do have an exam next Friday. I realized that today too when I looked at the schedule. But the nice thing is that exam's only going to be over a little over one chapter. It's going to go through buffers, and that's where it's going to stop. So it's only going to be a little over one chapter, which means it's going to be over less information than our first two exams were over. But that puts a lot on our third exam, so it comes back. Okay. So in College Chemistry 1, when you did acid-base neutralization reactions, you were primarily focused on the Arrhenius definition of an acid and a base. The Arrhenius definition of an acid and base is that an acid is a proton donor and a base is a hydroxide donor. This is quite limiting, because you got to have the hydrogen and you got to have the hydroxide. So it's actually a very limiting definition of an acid base. At the start of this chapter, we got into a broader definition of an acid and base, in that we started discussing the Bronsted-Lowry definition. And the Bronsted-Lowry definition is that an acid is a proton donor and a base is a proton acceptor. This actually opens up what can be described as an acid, because all it needed was a proton. And it opens up what can be described as a base because all it needs is to be able to accept that proton. So it's a broader definition, but the definition that is the broadest of the definitions of an acid base is the Lewis acid base definition. Where have you heard Lewis before? Lewis structures. Guess what? It's based off of Lewis structures. The Lewis definition for an acid, is that it's an electron pair acceptor. So it can accept a pair of electrons. Folks, technically, the Lewis definition also fits the Bronsted-Lowry definition and the Arrhenius definition for an acid because a proton can easily accept a pair of electrons when it forms a bond. So that definition those definitions fall under the Lewis definition. The Lewis definition of a base is that it is an electron pair donor. Well, it just so happens that the Bronsted-Lowry definition and the Arrhenius definition fit. Because if we have a hydroxide donor, that means we have a lone pair on that OH group. If we have a proton acceptor, that means that somebody had to have a lone pair in order to accept that proton. So the Lewis definition is by far the broadest. And actually, the Lewis definition is something that if you don't get a firm grasp on, it's going to haunt you in organic chemistry because organic reactions are mainly Lewis acid-base reactions. Or a lot of them. Meaning that they're all about that electron pair group. So let's start out just with some examples of materials. So classify the following. As a Lewis acid or Lewis base. The first one we're going to look at is pH 3. I'm going to remind you of your Lewis structures. You have one phosphorus. Phosphorus is in group 15. The last digit is a 5, so it has 5 valence electrons. You have 3 hydrogens. Hydrogen is in group 1. The last digit is a 1, so it has 1 valence electron. The phosphorus contribute 5. The hydrogens contribute 3 for a total of 8 valence electrons that need to be distributed around the molecule. The first element listed in the formula is typically going to be your central atom. The only exception is if the first element listed is hydrogen, but otherwise, the first element listed is the central atom, around which you're going to place all other atoms. You're going to draw a single bond between the outer atom and the central atom, and you're going to subtract 2 for each bond you drew. We drew 3 bonds. 3 times 2 is 6, so we will subtract out 6 electrons due to our bonds, giving us 2 valence electrons still to distribute. The next step in Lewis structures typically says to give your outer atoms an octet. Hydrogen only requires 2, so it already has its octet. The next step says if you have any electrons remaining, they go on the central atom in pairs. And so you have the lone pair that will go on the central atom in order to use up those 2 valence electrons. When you hit 0, you're to check, does everybody have an octet? The hydrogens do because they only require 2, and the phosphorus does because it has 8. So again, just reminding you of Lewis structures. Now, once you draw this structure, what you notice is you notice that phosphorus has a lone pair. Because the phosphorus has a lone pair, this is going to act as a Lewis base. Let's look at another example. Let's look at BCl3. You have 1 boron. Boron is in group 13, the last digit of 3, so it has 3 valence electrons. You have 3 chlorines. Chlorine is in group 17, the last digit of 7, so it has 7 valence electrons. The boron contributes 3 valence electrons and the chlorines 21 for a total of 24 valence electrons. The first element listed is going to be your central atom around which you're going to place all other atoms. You then draw a single bond between the outer atoms and the central atom, and you subtract 2 for every bond you draw. So we drew 3 bonds. 3 times 2 is 6. So we're subtracting out 60 electrons due to our bonds. That leaves you 18 valence electrons to go. The next step says to give your outer atoms an octet. Chlorine requires a total of 8 electrons in order to achieve an octet. So in order for these chlorines to get an octet, we have to place 6 additional valence electrons around each chlorine. 6 electrons times 3 chlorines is 18 electrons. And we are left at 0. Now, if we look at the boron, specifically, we notice that when we look at the boron, there is no electron pair. Therefore, that boron can act as a Lewis acid, and it can obtain an extra electron pair to make 4 bonds.
And you don't put like double bonds in order to build an octet?
Okay, so the question is, do you not add double bonds to make an octet on boron? And the answer is boron really only likes 6. So when it can make 4 bonds, but it's happy with just 6. So boron trichloride does not have 4 bonds on the boron. Now, folks, if you don't have to do the Lewis dot structure for every single thing. There are some things that are dead giveaways. First of all, a dead giveaway for a Lewis base is if you have an anion. And the opposite can be said to be true, that a dead giveaway for a Lewis acid is if you have a cation. So you don't have to always be prepared to draw the Lewis structure. It all depends upon what you're given. Let's look at an example. Let's take the reaction of carbon dioxide with hydroxide to form the bicarbonate ion. Because I have an anion, I can automatically label that anion as a Lewis base. And if it hasn't been, if I know I haven't said it, but if it hasn't been visually obvious, an acid always reacts with a base. So if the OH is the Lewis base, that means the CO2 must be a Lewis acid. Let's look at another example. 6 cyanide ions react with iron 3 plus to make FeCN6 3 minus. Here, again, what I notice is that cyanide is an anion. That's automatically going to make that a Lewis base because that means it has a spare pair of electrons in order to be an anion. And the iron 3 plus, the cation, is automatically going to be the Lewis acid because it is a cation. So sometimes it's going to be very obvious. Other times it's not going to be obvious. Cations and anions make it obvious. An anion is a Lewis base. A cation is a Lewis acid. But if it is not obvious, then you're going to have to draw the structure. Let's look at one more example. Let's look at H2O and SO3 going to form, let's see, H2SO4. Well, hopefully you have enough experience with water that you can do its Lewis structure without even blinking hardly. The Lewis structure for water has the oxygen attached to 2 hydrogens, and then on that oxygen are 2 lone pairs. Less obvious is going to be sulfur trioxide. Sulfur trioxide, if you were to draw out the Lewis structure, you would have the sulfur double bonded to 3 oxygens. And the reason for that is because of the formal charge. But did I really have to go through sulfur trioxide? Was that a necessity to be able to figure out this one? No. Why? The water had 2 lone pairs. So it becomes, with that in mind, this makes this, the water, the Lewis base, and the sulfur trioxide, the Lewis acid. Yes.
Is there ever a case where there's a lone pair and it's not the liver space?
If it has a lone pair, on the central atom, it will be the Lewis base. I'm trying to think through all of the possibilities. No, it'll fall into one of the categories. It'll either have a lone pair on the central atom or it will be a anion. Questions? On the test, you'll be given one or two reactions where I ask you to identify the Lewis acid and the Lewis base. That is normally what it is. Okay. So the next thing we're going to do is we're going to talk about salts. From College Chemistry 1, a salt is an ionic compound. Therefore, it contains a cation and an anion. Salts can be either acidic, basic, or neutral. Okay, so an acidic salt is going to be one where the acid making the salt was stronger than the base. A basic salt is going to be one where the base was stronger. And a neutral salt is the result of a strong acid reacting with a strong base. Now, the process for determining whether the salt is acidic, basic, or neutral.
or the simplest way. I won't say it's the only way, but it is the simplest way. To the cation of the salt, add hydroxide to make charge neutral. And determine if it is if the resultant material is a strong base or a weak base. To the anion of the salt, add hydrogens to make charge neutral. And determine if the resultant acid is strong or weak. We're going to do some problems here in a minute, but basically I want to give you a quick table. If you have a strong acid and a weak base, then it will be an acidic salt. If you have a weak acid and a strong base, then it will be a basic salt. If you have a strong acid and a strong base, then it will be a neutral salt. The question mark is what happens when you have a weak. And if you have a weak, then you look at the strength of the Ka and Kb. Whichever is larger will tell you what it's going to be. So let's put all this into action. And actually see this, see how we can determine our salts. So let's just start with a simple one, sodium chloride. To the cation, or the cation is Na+, and the anion is Cl-. To the cation, I'm going to add a hydroxide. To the anion, I am going to add a hydrogen. And then I'm going to look at them. In this case, I got a strong base and a strong acid. So this is a neutral salt. In order to answer that, you had to remember HCl, HBr, HI, HNO3, HClO4, and H2SO4 are your strong acids. Your strong bases are your group 1 oxides and hydroxides, as well as calcium hydroxide, strontium hydroxide, and barium hydroxide. If you don't remember that, you're not going to be able to figure this out. Let's look at the next one I have, which is going to be NH4NO3. I'm going to divide it into my cation, which is NH4 plus, and my anion, which is NO3 minus. To the cation, I'm going to add a hydroxide, so NH4OH. To the anion, I'm going to add a hydrogen, so HNO3. And then I ask, what is it? What is each one? Ammonium hydroxide is a weak base. Nitric acid is a strong acid. Because the acid is strong and the base is weak, this makes this one an acidic salt. Let's look at AlCl3. The cation is aluminum, 3 plus. The anion is Cl minus. To the cation, I add hydroxides to make it charge neutral. To the anion, I add hydrogen. Aluminum hydroxide is a weak base. Hydrochloric acid is a strong acid. So this makes that also an acidic salt. This is the easiest way I've found to do these, but you got to know who your strong acids and strong bases are. The next one, K2CO3. The cation is potassium. The anion is carbonate. To the cation, we add a hydroxide. To the anion, we add hydrogen. Potassium hydroxide is a strong base. Carbonic acid is a weak acid. Therefore, this is a basic salt. Okay, let's look at the next one. Let's do NH4NO2. The cation is NH4 plus. The anion is NO2 minus. To the cation, we would add a hydroxide group. To the anion, we would add a hydrogen. In this one, you're dealing with a weak base and a weak acid. So unless I give you the Kas, and Kb, it's inconclusive. In this case, it's going to be inconclusive because the table I have doesn't have ammonium hydroxide in it. Let me give you a couple to do. Go with that one and that one. And one more for you to work on would be this one. Yes. The table up here. Tell me when I'm good to scroll back down. Okay. There we go.
So for most week, can you give us conspicuous KA? Would you do expectations of song for KB?
Okay, I was just asked a great question. For the salt, the question I was asked is if I give you the Ka, would you be expected to calculate the Kb? Unfortunately, you cannot in this particular case because they are not conjugate acid-base pairs. That only works with conjugate acid-base pairs. So on the first one with sodium acetate, you should have figured out that it was a basic salt because it was basically made of sodium hydroxide and acetic acid. Sodium hydroxide is a strong base, acetic acid is a weak acid. For ammonium perchlorate, you should have figured out it was an acidic salt because ammonium hydroxide is a weak base and perchloric acid is a strong acid. And for chromium nitrate, you should figure out that it is an acidic salt because the chromium went to make chromium hydroxide, which is a weak base, and the nitrate went to make nitric acid, which is a strong acid, so it would be an acidic salt. Questions? If you haven't figured out, strong will out. The strong will out. Whatever's the strongest, that's what it is. And if they're both strong, then it's neutral. But in this case, whatever the strongest is going to determine the identity of the salt. Questions for me about Lewis acid bases or acidic basic neutral salts? This technically finishes chapter 16, and what we're going to discuss on Friday is buffers, which I was going to discuss yesterday in lab, but it all worked out. So I will go over buffers on Friday. And that will be where the test ends, is after Friday's information. Okay, the question was, how am I going to deal with lab? Basically, instead of your grade being out of 1,000 points, it's now out of 975, and you still get to drop your lowest lab grade. Yes. What? I have to work on those. I will get them out. I will try to get that done tomorrow at the latest and get them posted. It shouldn't take me long. I just got to do it.
So, if you want me to, because I seen in the right next to email it to, so you want me to print it out. Okay.
I'm barely here. I'm here.
I see you.
I'm here. It's what it is. Okay. Well, you get 1 point for every item. So if you only bring 7, you only get 7 points. No, then the max is 10 points. No, I said 5 extra if it's turned in tomorrow. So it's food pantry. Yeah.
There you go. 5 more kids.
Yes. Okay. No, it's 5 gotta make sure it's turned in by tomorrow because there's a food pantry push that's going on this week due to homecoming. And so we're kind of participating in that.
Okay.
I'll have to send you a photo. I'll try to do that this afternoon. Yes, I'll just print it off.
And then for extra credit, I saw somewhere, I can't remember where, but like you earn a max of 25. And there's like a bunch of opportunities you can't earn. It's like,
Correct.
You just do as much as you can.
Correct. And that way, the reason I have so many different opportunities to send that out. I know, like, you're on that.
Yeah.
You're talking, you don't necessarily, there's a thing tonight that you never know if you're, whether you're in the gym or what, would conflict.
Yeah.
So I give you as many opportunities as I can, and some of them don't require you to do something. And so I feel like that way everybody has a chance. And some people can't afford 10 cans of food to go to the food pantry. So they don't do that. So I try to come up with as many ways as I can. So you keep bringing me somebody else, huh?
What?
You keep bringing me somebody else, huh?
I know. He's like, I want to come. He's thought we were learning about buffers.
Yeah.
That will be Friday.
He loves buffers.
So we had I had to slow down a little. I was going with my original schedule since I wasn't here yesterday.
Yeah, I hope you don't mind.
No, I don't mind.
He loves chemistry.
Doesn't bother me. You too. Okay.
On this one, it says like pictures of us like doing it.
Oh, that will do until the very end.
Okay, and then also at the very end it says like after completing the lab, write this up. Like we should have like.
Well, no, you can do the exploration of the chemistry.
Okay.
The chemistry is what's going on.
Okay.
So
Just kind of explain step by step, like how the.
what is your topic?
The second.
Okay, so for you, it's all about hydrophilic, hydrophobic, solubility in water.
Okay, so just break that
So
down.
you're just writing out the story of the chemistry.
Gotcha.
Thank you. I was just trying to figure out, I couldn't figure out exactly what you were referring to.
Yeah, the pictures was the most thing for sure.
Yeah, the pictures are not until the end.
Okay. And we don't have to email to just leave it in the folder.
Yes.
Okay.
As long as I know which one to pull, we're good.
Okay. We just have it like labeled the ramp worksheet, ACS worksheet, and then we have like the